Hello and welcome to Electronics 8. So, this is going to be a recap episode, like every fourth episode in kind of academic series R. And yeah, it's going to be covering episodes 5 to 7. So, let's begin. So, electrons in different types of atoms have different degrees of freedom. It's kind of a term that's quite often used in robotics, actually, degrees of freedom, to move around. In metals, the outermost electrons are so loosely bound that they chaotically move in the space between the atoms of that material by room temperature heat energy. And this is a direct pathway based on the second law of thermodynamics, which is heat may be transferred from one body to another. So always speaking about transference, of course, and it's things like entropy and all this sort of stuff. So transfer happens via diffusion. So diffusion, of course, is a very powerful concept over all the sciences, really. Via diffusion of elementary particles such as electrons, other particles as well involved. More recently discovered quantum mechanical particles. So unbound electrons are free to move around in space between atoms and are known as free electrons. And something actually I was thinking about in chemistry here is, I didn't quite say it, but they're in the valence shell, the outer shell, and have a low ionization energy. It's known as the octet rule. I believe there are some exceptions to that rule. So, that low ionization energy is what allows these more modern electronic systems to work, because you're not requiring ridiculous amounts of power to get things done. Okay, and of course we mentioned in the first 4 episodes this whole thing with silk and glass and wool and wax and all that stuff. So in other materials, such as glass, the electrons in the atoms have got little freedom to move around. They're tightly packed. That's another key concept, sort of this packing concept, known as sphere packing, actually. But anyway, in the space where they rubbed, as mentioned previously, the electrons will transfer to that and the wax and will closely distributed. So what I mentioned is when they go to the so when we talk about static electricity, when they go to the wax, they're not just like moving all around the wax. They're just staying on that space where they were rubbed. So they're very, very closely distributed. It's like the accumulation, an accumulation of the electrons there, and often in computer science, for instance, you've got like accumulators you speak about. So there's another sort of, I guess that's just it's like an interpretation of that. So so the relative mobility of electrons within a material is called electric conductivity. So this is how mobile the electrons are. How are they? I mean, in static electricity, they're basically immobile. And they can't do much. But of course, that's not what the main focus of electronics will be. It will actually be ones that can move around, can be mobile. So conductivity is determined by the types of atom in a material. As we spoke about in chemistry, that's the atomic number. That's Z, isn't it? And the linkages between the atoms. So it's what's going to define the mobility. So it could be just, of course, just one, one type of atom, or it could be multiple as well. And in most cases, I think it is. So materials with high electrical conductivity are called conductors. So these ones, they can move around a lot. So they got the high mobility. They're called conductors. If they got low electron mobility, they're called insulators. They can't move around a lot. So it's more. So so it's almost like you can say, well, if they've got high conductivity, they're more mobile. Low electron, they're more insulating. So it's similar to. I mean, it's like dynamic and well, it is. It's dynamic and static, isn't it, in a sense? But yeah. So static is sort of like is the reason why you start on static is because you want the low mobility, and then you go to the high there. Okay. And then I've done this thing, Conductor Rankings. So like I say, I mean, so some of the stuff I've already spoken about, it's not quite exactly the same as what I said in 5 to 7. I've sort of appended a little bit extra to it. I like to do that in electronics. I actually did that in biology as well. I appended a little bit extra just to get that nice sort of flavour to everything that's going on here. and also, I mean, I suppose at the beginning of these things, it's always nice to add a little bit extra, because as you move on to more specialised things, adding extra is probably going to prove more difficult. So it's nice to just to to put a little bit of this extra stuff in. But yeah, the conductor rankings, and again I spoke about this, and I actually looked at this in more detail, and I wanted to find out what was the actual. Yeah, of course, I wanted to find out the ranking system. How well are these things ranked? These conductors, and yeah, and I did, like I said, I did speak about it, but I researched it further. So yeah, so silver is the best conductor, then copper, then gold, then aluminium, and then we've got brass, which is copper and zinc alloy. And then we had tungsten, which has got the chemical element W. I think it was also. I think it's called W because it's called wolframium or something. Yeah, yeah. So yeah. So anyway, so after that is zinc, then nickel, then iron, and then after that we've got steel, which is an iron alloy, mainly carbon there, and then platinum, lead, and then stainless steel, which is steel alloy, mainly chromium. So you can see there, you almost like can see like the development of the alloy stuff going on with. I mean, obviously this huge amount of work's being put into steel. I imagine that's to do with the. I didn't actually research, but I imagine it's to do with like the hardness or tensile strength, all that stuff. And they probably found it's so strong that they could make it a bit weaker, and it still will be enough. That is what you would think anyway. And over a little bit more, other conductors include bronze, which is copper alloy, mainly tin, mercury, which is known as quicksilver, and the deposits of it are found a cinnabar, mercuric sulfide. I think it's sulfide. Yeah, I think it's sulfide. Yeah. So graphite, which is an allotrope. Yeah, if you so allotrope of carbon. So if you look at so all this stuff like like Bravais lattices and all that stuff. That's where you get this allotrope stuff. That we get a different crystalline form. It's also very important in chemistry. This stuff, and it's where more of the advanced stuff comes in. Dirty water. That's electrolyte. So if you've got some wastewater might have like a biological, like electrolytic stuff. I suppose it's why human beings are electrolytic. It's why human beings are seen as electrical components. Well, yeah, kind of. I mean, well, no, it's true what I'm saying, but it's it's accurate what I'm saying. So it's accurate in terms of electrolytes, electrolytic stuff. You get electrolytic converters, don't you? Okay, and electrolysis, of course. With ionized atoms and stuff like this. Okay, so then we've got concrete as well. Calcium, silicon, aluminium oxides. Okay, so I guess an oxidation, I suppose, we'll still speak about in chemistry as well. All right, so let's move on a bit. So next thing, so insulators. I was thinking, how can I rank these as well? But I looked at it, and it turns out it's not quite as simple because you've got this thermodynamic stuff, like I say, which I mentioned, the second law of thermodynamics. And I did look at the insulating capability, the R value. A lot of this just seems to be involved with in terms of construction and building terminology, and various things to do with that. So it's equal to low thermal conductivity. And I was thinking at the time, it's quite hard to get it. You can say how good something is, but it's like, but here you're trying to say how bad something is. And in general, it's a lot easier to say how good something is than how bad something is, because it's much easier to determine how good something is as opposed to how bad something is. So obviously this is more complicated. Down to that basic, it's almost like a basic life fact, isn't it? So it's equal to low thermal conductivity, with density and capacity also playing a role. So there's multiple variables here. So you can't just it's not one size fits all in terms of Yeah, and now, yeah, and then you can think of many more things with that, and you sort of start thinking about elasticity and stuff like this. Yeah, I mean, lots of things to think about, I suppose. But anyway, so yeah, so what did I say? So commonly used insulators, and I did actually put them down anyway. I mean, obviously, like rubber and glass are very used. So you would imagine that. Yeah, just to try to get some kind of idea, you'd imagine that rubber and glass, these are going to be pretty high up on terms of insulation. Um, yeah, and yeah, so that's pretty cool. Rubber, of course, comes from trees, doesn't it? Um, so yeah, and oil, asphalt, fiberglass, porcelain, ceramic. Um, now, yeah. Now I remember, yeah. So basically, ceramic. You often see, don't you, on the actual resistors? They've often got this ceramic thing. It's not just like the exposed metal. Uh, so yeah, so that's probably why they're around the exposed metal, because of course for shielding. Yeah, I put quartz, dry cotton, dry paper. We didn't want to put. I guess the reason it's dry is because otherwise it's going to. It's not good to have the liquid. There are interesting properties to water, I think, which I need to look into that. But water can have interesting properties. But like I say, but pure water. So that would be distilled water, wouldn't it? In chemistry, that would be yeah. So it's going to be a good insulator. Diamond, of course, and you notice as well that with regard to this, the allotrope issue, diamond is also allotrope of carbon, but it's not on the same side. It's on the insulation side as opposed to the conductor side. So it's interesting. Yeah, so that's worth pointing out there. So okay, so the next thing to mention is yeah, electron motion is varied, with some conductive materials being better than others, and insulating materials not all sharing the same resistance to electron motion. So we're speaking about resistance, which of course is we're going to be speaking about a lot more with resistors. So yeah, and we can look at analogy with light. So with regards to transparency, so clear glass is better than fiberglass, for instance, in terms of the amount of light that can be seen. And dirty water and concrete are not as good as any metal. Metal are really what you want to be using. Of course, yeah, you really want to be using metal because they're the best at conducting things. Of course, maybe you don't always want the very best at conducting things, so we'll speak about that, of course, in future. So yeah, so like and yeah, and I've already alluded to this before because I actually gave the ranking system to say silver is better than copper, which is better than gold, etc. So yeah, now there are also other factors to consider, and of course when I was mentioning this about the insulators, with thermal conductivity, obviously this plays a role. So yeah, it's good to look at thermodynamics and all this stuff, and heat transfer, and all these, and the kind of the major laws and stuff there. So physical science is also key. So if we give, let's just move that down. So given all the other factors being the same, yeah. So of course, for any kind of scientific thing, you want to say we've got this control experiment, and then we can go off and do all the other things. So in this sort of control, idea, given all factors being the same, a thick strip of silver is a better conductor than a thin strip of silver. So yeah, so the physical size of that silver is going to be more important. And so a short strip is going to offer easier passage for electrons than a long strip of silver. You can imagine it's like traveling through a huge, the short strip is going to make it more easily because it's got less maneuvering to do. Okay, and again, heat is going to play a crucial role in the electrical properties. So glass, for instance, as an insulator at room temperature, becomes a conductor when heated to the high temperature. Yeah, I mean, there's a thing called liquid glass, isn't there? So gases such as air. So air, if you look at it, is was it seven? I think it's I know it's 70 nitrogen, 20 oxygen. Argon is about 1 or 2%. Carbon dioxide is about 0.5%. Yeah. So yeah, I mean, it's probably not the gases. It's probably that carbon there. But anyway, I mean, maybe you think about it. I mean, carbon does. I mean, we have seen that carbon is a a conductor in this in terms of graphite, but not for diamond, I suppose. In terms of the I mean, I'm sure there's a lot of different allotropes. I think there are a lot of different allotropes of carbon, and of course, carbon is is a main thing, isn't it? Carbon-based life forms. So yeah, but yeah, so air can be a conductor at high temperature. So yeah, I'm not gonna of course I'm not gonna go into the numbers and all that stuff. Because this is, like I say, this is, even though I am, this, because it's quite a general sort of thing. I'll just talk about some of these things, and I'm not gone too far with, going off topic. So yeah, so most metals become poorer conductors when heated and better when cooled. Okay, so yeah, so if you think about it, so things stop. So things stop working in terms of. It's why I suppose you've got like water cooling systems for computers and stuff like this, because then the metals are going to be working better. Obviously, that's with semiconductors, but I haven't gone into that. But I'm sure it's sort of the same thing anyway. But yeah, you don't want the metals to be very, very hot because they're going to become worse conductors. And sort of, I guess the entropy will increase. So yeah. And now here's an interesting thing. Many conductive materials become perfectly conductive at extremely low temperatures. This is known as superconductivity. So yeah, it's a thing you can think about, I guess, when you get this very cool stuff and you get a nitrogen stuff, don't you? And then it just freeze it all off once you put it in the big bucket of nitrogen, all the gas going everywhere. It's pretty cool. And then like you literally whatever you've got, it just it cracks into a million pieces. Well, I mean, into multiple pieces. So yeah, and the congruency here is the same as zero electrical resistance, and that's really what you want. Because if the insulator is providing resistance, then the perfect conductor is going to be one that provides nothing in terms of resistance. So that's perfect, and that's quantum mechanical phenomenon. And then what we talk about this field line thing, which is obviously a more complicated topic in electronics. And that's what it involves, as during the process, of course, the complete ejection of magnetic field lines. So that's a bit of electromagnetism stuff there. Okay, so and of course that being a major force. So yeah, as it was complete ejection of magnetic field lines undergoes the process. So electrons wander through a conductor fairly randomly with no particular directional speed. So it's just a meander through. But their movement can be coordinated, and this is where, of course, you start to think, you could actually build a system out of this. So when it's done, it's known as electricity, electric current. Now, unlike the rubbing in static electricity, where there's just a build-up of stationary electrons, as I mentioned, so that shows dynamic. So now we're speaking about dynamic electricity, not just static electricity, it's dynamic electricity. Okay, so electrons are able to move within the empty space, within and between the atoms of a conductor. So of course we always have to think of everything as empty space. Everything is kind of empty space, and yeah. So anything that we see as a solid object is kind of just like an illusion sort of thing, and involved with the inability of our eyes perhaps to actually see what's going on here. In terms of, there's an inability in terms of the degree and the magnitude of clarity, isn't there? In a sense, so it's the magnitude of the I mean, I kept on wanting to use the word interstitial space. I quite like that word interstitial, but it's not really. Unfortunately, it seems to be part of a more advanced topic, so I can't really use that. But I would like to use it anyway. But anyway, so the point is, right? The analogy with pipes is further extended here. That the electric current, as it moves around the empty space in the atoms, is called the flow. So all the electrons moving around is the flow. So of course, so if you imagine what we spoke about before, this analogy with the pipe system, this is you literally there's I mean, yeah, you can imagine it like water moving through, and that's why it's called the electron flow. How does these flow? But yeah, but of course, right? You know, but then you got to think, well, what is this flow then? Is it just like little electrons everywhere, just going through? How they? I mean, they're not even. You know, it's just is it there different lines of it going through? They're different. You know, and this is where you start thinking about how are these electrons moving through? Are they moving through one by one? They're moving through a million by a million. You know, is it you know these lopsided? Is it two by a million or a million by or a million by 500,000? What's the ratio? You know, all these things you can think about, I suppose. But yeah, but here's the thing. So as each electron moves uniformly through the conductor, it pushes on the one ahead of it. Okay, so I thought well, this here. I thought about ants, which is probably, I mean, yeah, because I mean, how the ants manage to do a leaf. I imagine. I mean, I haven't actually looked into this too much, but I imagine that probably the head of one ant is pushing the tail of the other ant. And similarly, like for birds, because I know that birds they've got air sacs on their back. Yeah, I think I'm not quite sure how they get their air, but I think the air actually comes in through their back with birds. And that's probably how they keep pace with each other. So similar to like ants and birds and all that, and all those sort of like like advanced creatures and stuff like that. So yes, but anyway, the point is is they push on the one ahead of it such that all the electrons move forward as a group. Okay, so the start and end points of electron flow through the length of a conductor is virtually instantaneous from one end of the conductor to the other, even though the motion of a conductor may be very slow. So yeah, so when you move as a group, it's the motion of individual things is kind of becomes negligible, and the group is what matters. So yeah, and so if you think about if you've got a tube with marbles filled all the way through, and this is a closed tube, right? So nothing can go in. There's only two spots. There's an input and like an output, and nothing can go in or out the tube from any other places apart from the input and the output. If you've got say 10 marbles in that tube, and they're in the tube, the left hand side of sort of the first marble is matched up to the edge of the tube there, and similarly and vice versa for the right hand side. If you then put in this next marble, what's going to happen is the marble on when you put it in the left hand side, the marble on the right hand side is going to come out almost instantaneously. Yeah, and then like I say, and that's going to be irrespective of the length of the tube. So that's kind of a important point there. Yeah, and of course with electricity, it's quite accurate, isn't it? Because the speed of light is 186,000 miles per second. So yeah, so that's why that's similar. The electrons do travel more slowly, however, though. But yeah, I mean, so that's all I really wanted to talk about, I guess, for electronics A. Going to move on to different topics coming up. So until that time, thanks for watching.